All right, we are live. Welcome on in, everyone. Robert, the AP Math Guy, and tonight we're going to be talking about this thing called differentiability. So, as you join in, please go ahead and hit that heart button. Let's see. Let's see if we can't get to 1,000 before we get started tonight. Hopefully, everyone's had a good Monday evening. Or for me, it'll be Tuesday morning here soon. Yeah. I'm going to go ahead and spend the next few minutes just waving at everyone coming in. But if I can't wave at you by pressing the button, I will go ahead and wave to you now. Hi, everyone. So as you can see up at the top of your screen, tonight I think we're getting the 2,000 followers. Hence that meter at the top of your screen. My goal was to hit 1,000 by the end of the year, and we crushed that goal about a month ago or so. Now here we are, getting ready for 2K. Tonight we're going to talk about something that I think I skipped over, but I think it's going to be important, is differentiability. And I think it's really important for us to tell where a function is differentiable, because it's going to help us tomorrow when we talk about sketching graphs of derivatives. And speaking of that, we haven't updated our checklist in a while. So, we did extreme value theorem already, so we'll go ahead and check that. We did it on the same night that we did critical point, so we'll go ahead and check that. We did concavity on Saturday night, so I'll go ahead and check that off. And I'm saving this for tomorrow. No sound detected. What do you mean no sound detected? Can anyone hear me okay? Can everybody hear me? Now I'm kind of worried that um I'm just talking to myself. Thank you, Blue One, for liking the live. Right now I'm just trying to do a quick sound check. If anyone can hear me. Thank you, Blue One, for the 2 roses. Hey, Ang. How's it going? Can you hear me okay? You can hear me. Awesome. That means other people can hear me. Thank you, Blue One, for 2 more roses. Awesome. So, yeah. So, let me go ahead and slide this over a little bit. Yeah, like I said, hopefully everyone's having a good Monday evening. And also for me, it's going to be Tuesday morning here in about 5 minutes or so. That's always fun. But yeah. So let's go ahead and get started. So really when we talk about differentiability, we're linking it to continuity. So remember, how do I know a function is continuous? I think you swallowed the pills for the follow. 7 more to go until we hit 2000. So let's go ahead and define continuity. So a function is continuous if the following 3 things are true. 1, the limit as x approaches c of f of x exists. 2, f of c exists. And 3, the limit as x approaches c of f of x is actually equal to f of c. If those 3 things are true, then the function is continuous at c. So how do we know that the limit as x approaches c of f of x exists? Well, remember, limit as x approaches c exists if, or I need to include my function, that should be f of x. If the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. So if these 2 things are equal, then this limit exists. Oh, we got another follower. I don't know who it was, but thank you for the follow. So, if this is true, then condition 1 is met. Condition 2 is met if the function exists at that point. So let's take a look at a graph and show you what I mean. So, oh, by the way, I found my ruler. Let me go ahead and attempt to draw this. So that's my x point. This is my xy plane. Thank you, Not Tommy, for the follow. How do you define a limit? Okay, yeah, so the limit, so quick review. The limit as x approaches c of f of x, all that means is as x gets infinitely close to some x value, c, what does y get closer? What is y approaching? That is called the limit. So sometimes the limit as x approaches a number of a function is not actually equal to the function at that point. So all the limit cares about is whether or not what value of y we're approaching as x approaches c. Good question, Public Sphere. So anyway, back to this. So let's say I have this function. Thank you, JD Poe, for the follow, and thank you, D, for the follow. Does it have a min-max? Does what have a min-max? is there a rigorous definition? How would one know y is there a rigorous definition? How would one know y if x is infinitely close to c? Well, we don't, like that, we don't actually care about what the y value is. All we care about is what y approaches. So here, I'll show you this. So let's say I'm going to name this point A. Thank you, Yasmin, for the follow. So, as I approach A from both the left and the right, we see that it approaches this y value. Now, if we look, we have an open dot here and a closed dot here. This is a discontinuity. So this function, because of this, because it does. So actually, let's test this. So, does the limit as x approaches c of f of a exist? Of f of x exists at a? Yeah, it does, right? Why? Because as I approach from both the left and the right, I approach this open dot. So we can check that. Now, does f of c exist? Or f of a in this case? Yeah, it does. It's this closed dot here. Now, does the limit equal the actual value of f of a? No, it doesn't. Because this open dot means that this point is not part of the function. Instead, what I did was I took this point, removed it, and moved it up here. So you're right, actually, it is not continuous. You're absolutely right, Ashley. So this function would not be continuous. This is what we call a removable discontinuity. And remember, there are 3 types of discontinuity. So let's write that down. 3 types of discontinuities. Discontinuities. So first is the one we just saw, which is a removable discontinuity. Discontinuity. After all these years, I still have to think about how to spell these words. Nuity. And then the second type of discontinuity is what we call the jump discontinuity, or as I like to call it, the Van Halen discontinuity. Because in the 70s or 80s, Van Halen came out with a song called Jump. So that's why I call it the Van Halen discontinuity. And the third type of discontinuity is called a infinite or non-removable discontinuity. And yes, I am using a erasable pen tonight. So these are the 3 types of discontinuity. Oh, we're 1 follower away from 2K. Let's go. So, these are my 3 types of There we go. Thank you, Hubble Star, for the follow, and thank you all for helping me break... Excuse me. Helping me break 2,000 followers. There we go. We have broken 2,000. So again, thank you so much to everyone who has joined me in this journey so far. Like I said, my goal for the end of this year was to break 1,000. And tonight, with 3 months to go, we broke 2K. So this is now becoming a thing. So thank you, everybody. Thank you, Pixel, for the follow. You have to break 3K next? Absolutely, that's the goal. That is the new goal. Hey, Brainsy, how's it going? So I have an update on the exam. Cool. How did it go? Also, thank you, Loyal Lewis, for the 7 roses, the 5 finger hearts, the 5 it's corns, 5 chilies, and 10 you're awesomes. Thank you so much, Loyal Lewis, for that. You got an 84 brand? That's awesome! Congratulations! Way to go! Way to go, Brand Z. You know what, Brand Z? That deserves a high five. Are you ready? On the count of three, we'll high five. 1, 2, 3. Yeah. Thank you, Loyal Lewis, for the follow. My class average for the first Cal exam. Ooh. That's not good. That is not good, Paulina. It must have been a really hard. It must have been a really difficult exam. If that's the class average, if I all right, so here's my thing. If I were when I was back in the classroom, if I saw that was my class average, I'd be like, yeah, we're gonna go back and review some stuff because obviously I didn't teach it well enough. Yeah, that is that yeah, that's not good. You're right, Hermione Granger. That is a removable discontinuity. Thank you, R, for the follow. I'm so glad I passed this class. That's awesome, Gunslinger. Way to go. Or maybe it was taught by a teacher who teaches math, not a math teacher. Fair enough. That's mostly right, Hermione. That would only not be true if if this third condition was met. Can you do annuity problems? So I'm gonna focus on differentiability tonight, but let me add annuity problems to the list because I think that's a really important topic to go over. So, annuity problems. Actually, how many of these have I covered anything more since I last looked at this? Nope. So, correct, and I agree with you, Hermione. The thing is, the way the that is that is correct. You are right. I'm just saying that just because these two limits approach the same point doesn't mean that it's always going to be a removable discontinuity. But yes, you're exactly right. We agree because sometimes it's not even a discontinuity at all. Do you go over finding limits algebraically? Had my first calc exam today and got confused with conjugation. Yeah. So, and actually, you've covered L'Hopital rule already in this live. Yep. Well, yes, exactly, Hermione. That's absolutely right. So, here So yes, I to answer both of your questions, yes, I did. And in fact, you can find those lives here on this channel over here. Thank you, Mark, and thank you, Breon Miller, for the follow. Awesome. Well, let's do SR. If you want, you can stay and watch this and watch that video at the same time. Thank you, Math Scribbles, for the follow. So yeah. So that's a little quick review on discontinuities. Now, let's talk about differentiability. So, how do I know if a function is differentiable? So, let me write that here. So, differentiability, how do I know if a function is differentiable? Thank you, Math Scribbles. I will. Can we go over the Stone-Weierstrass theorem for polynomial approximations of continuous functions? I don't. I have to admit, I don't know what that is. Let me just do a quick lookup of what it is because I have never heard of that in my life. So let me look that up and then all right. The Stone-Weierstrass theorem is a vital result in the study of algebra of continuous functions on a compact Hausdorff space. Okay. Yeah, that would explain why I have never heard of it. So how do I know if a function is differentiable? Its derivative or instantaneous rate of change exists at every point in its domain. Yeah. Yeah, so not only that, but there's a link between continuity and differentiability. So f of x, f of x, in order for a function to be differentiable, the derivative has to exist at every point in its domain. Not differentiable when no sharp corners are vertical. Exactly. That's exactly right, Loyal Lewis. You all are ahead of me a little bit. That's awesome. Oh, I just thank you, Math Scribbles, for the rose, and I can't believe I just missed the galaxy. Thank you, Math Scribbles, for the galaxy. Whenever I join this live, you go over exactly what I'm. Wow, wow, that's crazy, Shem Tov. That is really crazy. Thank you, Taco, for the follow. But yeah, so how do I know? So f of x is differentiable if the derivative exists for all x in the domain. In the domain. Right now I'm struggling with Riemann sum. I'm missing derivatives. You're doing Riemann sum already? Are you taking Calc 2? You must be taking Calc 2. Otherwise, Cal 1. Okay, cool. In September? Thank you, Meaty, for the follow. So, that's interesting, Lewis, because can you follow me? I want to support you. Um, let me. I'll have to take a look at. I'll have to take a look at your content. Um. So yeah, how does that work though? How does it work that you're taking your finals in October? Now I'm genuinely curious. So let's talk about. Nope. Let me move that over here. So how do I know if f of x is differentiable? How do I know? Ah, that would make sense. Is it like one of those 8-week courses? Ah, okay, interesting. Very that would explain it. I was like, that's interesting, but no, that makes perfect sense. That makes a ton of sense. So yeah. So how do I know that if the derivative exists for all x in the domain? So if we're looking at a graph, we're looking for two things. A, so let's look for what makes f of x not differentiable. What makes f of x not differentiable given the graph? Well, there are two things that we need to look for. So I'll give you an example. I'll give you a visual example of both. Or actually, well, I'll get to that in a moment. So, one, the function can't do something like this. Nor is the function differentiable if it does this. Let me move that up a little bit. So what do we notice here? Well, let me see the graph, please. Sure. It's right. Both of them are right there. So, now, what do we see? Well, this is a cusp, or as I like to call it, a wave. Also, so what I've also seen people call it, I also call it the sword, right? Because sometimes you're going to have a function that could also look like this. So anything that has a sharp edge or a wavy cusp, the derivative doesn't exist here or here. And why is that? Well, a we have a vertical slope, we have a vertical tangent line at that point, but even if that weren't the case, there's a rule that says that if I go from a positive slope to a negative slope or vice versa, at some point the derivative must equal 0. But at either swords or waves, there is no point where the derivative is 0. So a function, so here, neither of these are differentiable. Why is the tangent line vertical at the peak? That is a good question. The reason why the tangent line is the reason why it's the reason why our tangent line is vertical here. Actually, let me just I am drawing a blank for some reason. So yeah, so the tangent line actually isn't defined. So I'm going to erase those. But the idea still holds because we have a sharp because we have a sharp switch from positive to negative slopes, or like here, same thing. We are not differentiable here. And the reason number 2 is not differentiable is because we have a vertical slope here. Thank you, S, for the follow. So yeah. Also, the other rule we have to know for tonight is this. The rule that we need to know is that if a function is differentiable, it is automatically continuous. Whereas if a function is continuous, that doesn't necessarily mean that it's differentiable. So, continuity, or let me write it this way. Differentiability implies continuity. So if a function is differentiable, it automatically is continuous at that point. Or if a function is differentiable at a point, it's automatically continuous at that point. However, continuity does not imply differentiability. So just because it's continuous doesn't mean it's differentiable. But if it's differentiable, we can say that it's continuous. So yeah, any questions so far? Any questions so far? I don't see any, but just because I don't see any right now doesn't mean that you don't. So if you're typing out a question, please feel free to continue. I'm going to go ahead and turn the page, and so we can do a few examples. So actually, I'll write that down on a note card too, so that way we can have, that way we can, I don't have to flip keep flipping back and forth. So, that over here. Did I run out of note cards? I might have. I might have to go to the store and get some more. But for now, let's actually use... Or actually, let's use this. So, continuity implies differentiability. So if a function is not continuous, it's automatically not differentiable. Is this for Calc AB or BC? Both. Everything in Calc AB appears in BC, but not everything in BC appears in AB. So differentiability does not imply... Oh wait, no. This should be the other way around. So we'll get rid of that. Oh, I found some. So if differentiable, then continuous. If continuous, then not necessarily differentiable. There we go. My school makes me take both, so I'm in AB now as a junior. Okay. How's it going, Mason? How is that class going for you so far? So, we're going to look at some graphs tonight, and we're going to see whether a function is differentiable or if it's... So I'm going to ask you if it's continuous at a point and if it's differentiable at a point. Let's look at example 1. So, let me draw that graph. All right. I have a test on this on Wednesday. I'm missing class tomorrow, so I need to lock in. Excellent. Hopefully everything's okay, though. So, I want you to determine the following. So, at x equals 3, is this function continuous, differentiable, both, or neither? What do you think? Mason says not continuous, so it's not differentiable. That's right, Mason. So it is neither continuous nor differentiable. That's right, Mason. So it is neither. Cool. Do we see how that's the case? Actually, let me rewrite the three conditions of continuity here. Although I thought I had that note card somewhere. Continuity. 1. So those are the three conditions of continuity. So here, does f of 3 exist? It does. Does the limit exist? Well, from the left, I approach this value, and from the right, I approach that value. So the limit does not exist. So because it fails number 2, this is automatically not continuous. And since, in order to have differentiability, I have to have continuity, that's how I got neither. You should make the AP videos for calc. I'm actually working on some right now. Let's go ahead and try another one. Let's try. Let's take a look at this. We'll let this value be C. This is my this is the part of the this is the part of the live where I warn you my drawings are terrible, so please forgive me if I can't if it looks like I can't draw to save my life. Yes, we can assume it's a parabola. This is not a very good drawing of one, but this is a parabola. Yes. Is the function continuous, differentiable, both, or neither? Don't you list those 4 choices? Hey, Imperfect, how's it going? Or is f of c a continuous, b differentiable, c both, d neither? Imperfect says both. Beefer says both. Mason says both. Yeah, you're all right. That's exactly right. It is both. Why? Because A, I can't draw, but B, if we look, does it meet the 3 conditions of continuity? Well, step 1 is that f of c exists, which it does. It's right here. Does the limit exist? Well, I approach the same y value from both the left and the right of c, so yes. And does the limit as x approaches c equal f of c? It does. So this is continuous. Now, how do I tell if it's differentiable? Well, it's differentiable if I don't have a cusp or a sword, or if we don't have a vertical tangent line. So if I were to try to draw the tangent line, and emphasis on the word try, let me attempt to draw this because, as we've clearly established, I'm not very good at drawing. I don't know about you, But that tangent line here doesn't look vertical to me, and I don't see a sword or a wave at the or a cusp at that point. So it must be differentiable. So yeah, the answer is C. It is both continuous and differentiable. So both A and B, neither A nor B. Do I think I would have helped invent calculus if I was back in the Leibniz Newton times? That is an interesting question. Like if I knew what I know now, or because I'll admit this, Leibniz and Newton were both a lot smarter than I am. No, no, I wouldn't have. Like that, those two were much smarter than I. Much smarter. So yeah, that is our answer. Thank you, Mason, for the follow. Let's try another one. I am a learner. I am too imperfect. I try to learn every day. So I gotta go, but have a good night, Mason. Thank you for joining us tonight. You'll definitely stop back in again? Perfect. We will see you next time then. So, let's say I have a function that looks like this. Is f of a continuous, differentiable, both continuous and differentiable, or neither continuous nor differentiable? Josh says continuous. Shem says neither. Imperfect says A. Josh says A. Beefer says A. Yeah. So, so first, does it meet the criteria for continuity? What do you think? Does it meet the? Hey Henry, how's it going? Beefer says yeah, left-sided and right-sided limits match, right? And f of a is the same as that limit, right? So yeah, it is continuous. Is it? How do I know it's not differentiable? Very well. You're welcome, Henry. I'm glad you're doing well. So how do I know that that is not differentiable? Well, it's because I go suddenly from a positive to negative slope without a point where the slope is zero. So here it looks like I have kind of like a shark fin, doesn't it? Or maybe like a yeah, I think shark fin is probably the closest thing to what that is. Oh, actually, let me attach my arrowheads. So because I have a sharp point, this function is not differentiable. So it's continuous, but not differentiable. Very good. So here's a question. Can a function ever be just differentiable and not continuous? What do we think? Can a function ever be differentiable but not continuous? Henry says no, and I would agree. Yeah, no. A function can never be differentiable but not continuous. Because remember, if a function is differentiable, then it implies continuity. Because continuity, because derivatives don't exist where a function is not continuous. Let's try one more of these, and then we'll look at some functions and see how to find whether the function is differentiable or continuous. Hey, Space Cowboy. Hey, Space Coyote. How's it going? I almost called you Space Cowboy there for a second. I don't know why. All right, so let's move the graph up here. And let's say we'll say this. Hey, Mukhtar, how's it going? Kind of sine, not necessarily sine. It is kind of sinusoidal, yes. If it were sine, then my peaks and my valleys would be the same all across. Whereas here, this peak is higher than this peak, but this valley is higher than that valley. So what do we think? At A, is this function continuous, differentiable, both continuous and differentiable, or neither continuous nor differentiable? What do we think? Here are your choices. Here are your choices. If I can attempt to do this without covering the graph. There we go. Blessing says both. Hey, Blessing, how's it going? Mukhtar says both. Hey, KG, how's it going? Welcome on in. Henry says that's a hard one. Okay. Give it a try. Henry says B. Okay. Well, remember, Henry, we can never have a function that's differentiable without it being continuous. If a function is continuous, it's differentiable as well. So, not necessarily. Do you do this every night? I need help with implicit differentiation. I do. However, I already did a live on implicit differentiability, and you'll be able to find that live. Let me zoom out a little bit. You can find it here at that channel. So yeah. So here, I don't have a spike. I don't have a sword or a wave or a vertical tangent line, so it's definitely differentiable. And because it's differentiable, it automatically is continuous. So my answer is both. Continuous. Continuous. Might help if I spell correctly. Both continuous and differentiable. Cool. I just realized I wrote that right underneath the meter. Any questions on that? All right. Fair enough. Do there exist trig functions like this where the amplitude decreases gradually? I think so. I just can't remember how to create them. So you're thinking of something like this. So let's say I have something like this where I have that and then kind of like that. Again, this is my best drawing of one. I can't, as we've established, I can't draw. Yeah, so they do exist. I don't know how to how to actually create them. I've never taken this, and at 50 I still like to learn. Absolutely, Henry. There's no, and I mean, we should all strive to be lifelong learners, right? Because even we're always learning. That's what makes us better people. But yeah, hell yeah, that's absolutely right. I need to relearn Fourier analysis for a class. Will you do them soon? Fourier analysis. I think that would be. Let me take a look. I think Fourier is going to be a little while. Yeah, it's gonna be a while. I think I have that on my list though. Let me check the list. Here's the list. Yeah, I have Fourier transform right there on my list of things to cover. Thank you guys. You're most certainly welcome, Henry. You're most certainly welcome. So let's go ahead, turn the page, and we'll talk about when we're not able to see the graph, because sometimes we're not going to be able to see the graph. Let me move that out of the way. Let me bring this back down. There we go. Let's take a look. Let's take a look at the following function. So f of x is equal to x squared minus, not plus, minus 6x plus 1. So I need to know, is this function continuous, differentiable, both, or neither for all x? So, is f of x continuous? And is f of x differentiable? So, when we think about continuity, remember the three conditions that need to be met for continuity. Or actually, let's do this first. Let's test for differentiability, because if it's differentiable, then it's automatically continuous. Imperfect says both. Let's see if you're right. So here, what I'm going to do is I'm going to take the derivative of this function. So in order to do that, I'm going to use this thing called the power rule. And what does the power rule say? The power rule says that if I have a function, if I have a variable raised to a power, its derivative, I take the exponent, move it out front, multiply it by whatever coefficient's in front, and subtract the exponent by 1. So following that rule, if I have a derivative, if I want to take the derivative of x squared, what I'm going to do, take that 2, move it out front. So there's a 2. And then I have x to 2 minus 1. 2 minus 1 gives me 1. And a variable with 1 as its exponent is the same as a variable without the exponent. Thank you, Sam, for the follow. When you have an important game, I will help you win. Okay. Okay, then. So, here, as I said before, variable without a power is the same as variable raised to the first. So I have 1 times a negative 6 gives me negative 6. And then I have x to the 1 minus 1 power. 1 minus 1 is 0. And remember that x to the 0 is equal to 1. And then I have plus 1. Now, I don't see a variable here next to the 1. So 1 is what we call a constant. And the derivative of a constant is equal to 0. So the derivative is equal to 2x minus 6. Bro, please help me. You have midterm tomorrow. I don't think I have a midterm. You have a midterm tomorrow. Okay. Okay. So hmm. Hmm. So are there any particular topics on your midterm that you're struggling with the most? Colin says yes and yes. So yeah, so here, what I need to do is I need to look and see if my derivative exists for all x in the domain. Well, I don't see an even root. So here's what I'm looking for. What to look for? 1, any even power of x, any even root of x, or 2 something over x. Because here we have potential for, so for number 2, we have potential for division by 0. And for number 1, we have the potential of I. And those two things are not allowed. So if I have I or division by 0, then the function, then in the derivative, that means the derivative doesn't exist at that point. Do you see either one of those things here? Do you see either 1 or 2 in this derivative? Evaluating composite trig facts or functions. I'm not sure what that abbreviation is. Imperfect says no. Beaver Jones says no, since it's just linear. Yeah, exactly. So I don't have a square root around that x, nor am I dividing. Nor do I have any chance of division by 0. So the derivative exists everywhere. So therefore, is it differentiable? Yes, it is. And by that virtue, is f of x continuous? Because it's differentiable, it is also continuous. Functions. Okay. Yeah, no problem, Limon. No problem at all. Yeah, I do agree. They can be tricky. Are you looking to do... What are you looking for? Oh, you're looking to evaluate them. Or are you looking to take derivatives? Yeah, no, I don't think he's looking for taking the derivative. I got a 93 out of 100 on my limits test. Your tutoring helped me to visualize better. That's awesome, J Rogue. Very good. I am proud of you. You know what that means, right? That means high five. All right. So, Jay, on 3, I will go ahead and give you a high five. Ready? 1, 2, 3. And I just accidentally shut my light out. That high five was too powerful. It was so powerful it cut the lights. Awesome. Yes. Thank you, Hi, for the follow. He's talking about evaluating them. So if you had something like, so you're talking about something like sine of cosine of x, as you said in your example. Oh. Oh, okay. Yes, but more like sine of arc cosine, where x can be any number. Okay, so tonight I'm focusing on differentiability. But if you want, send me a problem, Limon, and send me a DM with a problem, and I'll be happy to help you with it. Yeah, no problem. So, let's go ahead and try another one. So, you have f of x is equal to the following. I have to make sure I get my signs right. So, So I have the function f of x is equal to x squared minus x minus 12 all over x, the quantity x plus 3. So again, we ask, is f of x continuous and is f of x differentiable? Do you see what I see? When it comes to this problem? Imperfect says not continuous on point -3. Why is it not continuous? You're right, it's not continuous, but why? I can only see x cannot equal -3. It's a removable discontinuity. Why? What rule does it break? Can't divide by 0, that's right. So if I plug in -3 for x, I get -3 squared minus 3 minus 12. -3 all squared is 9. 9 minus -3 is 12. 12 minus 12 is 0. -3 plus 3 is negative is 0. So I have 0 over 0. But even if I had some other number divided by 0, it's still not continuous. So it's no. And because it's not continuous, it automatically cannot be differentiable either. So, how do we know it's a removable discontinuity? Well, let's factor this top trinomial. So I'm looking for two numbers that multiply to -12 and add to -1. What are those two numbers going to be? DJ says -4 and 3. Imperfect says 3 and 4. All right. So we agree on x plus 3. B first says -4 and 3. Yeah. So here, it's -4 because I have two numbers multiplying to -12, so that's going to be one positive, one negative. And because this is a negative, that means the greater number is going to be negative. So I have x minus 4 times x plus 3. So now, so now from here, can you read my reasoning and see if that's correct? I don't see any, I don't see it. All I see is of a discontinuity. Euler's number. Charles says sine squared plus cosine squared. Nope, it's not 1. Scroll higher. Okay. All right. Let's see. No, it's not there. Yeah. So here, so all I see, so I scrolled up a little ways, and all I saw from you was of a discontinuity. So here, yeah, I have an x plus 3 in the numerator and an x. Yeah, it might be filtering her comment out. I'm not sure why it would. So here, I have an x plus 3 on top and an x plus 3 on the bottom. So here, I can cancel these out, but because I can cancel these two out, a hole exists where that equals 0. So x plus 3 equals 0. Subtracting 3 from both sides, there's a hole at x equals negative 3. This is a removable discontinuity. So therefore, this is neither continuous nor differentiable. If there's a hole, it's discontinuous, therefore it's not differentiable. You're right. Absolutely. That's absolutely right. I think that it's Sana. Mister, I'm going to fail my discontinuity test. I hate trig derivative. Wait, not discontinuity. I meant derivatives. Okay, so let me go ahead and show you something that might help. So here is a list of all of the 6 trig derivatives. So if you want, go ahead and take a screenshot of those. Yes, it can. Perfect. Perfect, Sana. Awesome. What does differentiable mean? That's a good question. So all it means is that we can draw the tangent line. Do I tutor online for Calculus AB? I do indeed. If you're interested in online tutoring, feel free to DM me and we'll schedule a free consultation. I remember my teacher telling us to memorize them. Okay. Do you do any circuit analysis? That sounds difficult. Is that an engineering thing? I'll do that. Thank you. You're welcome, Sana. Yeah. So nope, I don't do any. This is the furthest I go into the math portion of engineering, like calculus and differential equations, is the furthest I go into engineering. When it comes to the application stuff and like circuit analysis, I wouldn't have a clue. I have to admit, I would not know how to even begin. So, given that a lot of people given that a lot of people on here ask me about engineering, maybe it's something I should look into, see if I can't learn some stuff. OMG, the trauma is coming back a little, but I can't stop watching. Good one, Gizmo. That's really good. I'm in differential equations right now, but it's kind of easy, not gonna lie. I'll be honest with you, I actually struggled through differential equations. And it was difficult for me, yes, but it was also me making the mistake of, oh, this is gonna be easy. Um, I took Calc 1 and Calc 2 my freshman year of college. Practically slept through both of them. So I'm like, oh, if math in college is going to be this easy, then I really don't have to try. And then I ran into differential equations. Yeah, that taught me a lesson quickly. You're taking Calc AB right now, your senior year. That's awesome, Sana. That's really cool. How's it going so far? So anyway, somewhat difficult. My teacher isn't. Oh, I'm sorry to hear that. Can you explain how to derive 2 times cosine of 2x. Are you talking about taking the derivative? Well, actually, that kind of makes sense that you are. So here is how you do it. You're going to do something called chain rule. So chain rule says if I have a function trapped inside another function, what I do is I take the derivative of the outer function, leaving the inside alone, and then I multiply it by the derivative of the inside. So, can we do a chain rule problem? Tonight I want to focus in on differentiability. That's right, Dave. That is absolutely right. But tonight I want to focus on differentiability. But I already did a live on chain rule, and you can find that live here on this channel. I'll give everyone a moment to take a photo of that. Then I will work on the last 2 problems that I have. Five, 4, 3, 2, 1. All right. So we're going to do 2 more problems, and then we're going to call it a night. Let's try. Why don't you cancel the x plus 3? We can. We definitely can. I'm just saying that when we do that, when we're testing for what type of discontinuity it is, if we cancel, then there's a hole where this is true. Thank you, Kay, for the follow. Yeah. So yeah, we would cancel the x plus 3. But I just wanted to show you that, too. Alright, so this is perfect. I have a Calc 1 exam tomorrow at 1. Okay, Connor, best of luck to you. Hopefully, I'm sure it's going to go great. Alright, so let's try f of x is equal to, oh, this is a really fun one, sine x over x. Thank you, Lorena Lopez, for the follow. So, is f of x continuous? If so, is f of x differentiable? PTSD just kicked in. Sorry about that, J-Rogue. Thank you, Ness, for the follow. Alright, so, is this a continuous function? Number says yes. Mikey says no. Looks like we have a bit of a disagreement. J Rogue says no. Sam says sine is continuous everywhere. That is true, but is it just sine x, or is it all of this, or is it being divided by x too? Imperfect says no. Jay says sine is continuous, but the denominator can equal 0, right? Mark says L'Hopital's rule can help us here. No, it cannot, because we're not taking a limit. Sine also loves oscillating. Yep, sometimes it does that. Yeah, so yes, it is differentiable using squeeze theorem. So squeeze theorem helps more with limits um rather than just a regular function. So the answer here is no. This function is not continuous everywhere. In fact, f of x is not continuous. Continuous at x equals 0. Why? Because if I plug in 0 and 0 here, what do I get? I get sine of x, which is 0. 0 over 0 cannot be. So this is not continuous. The limit will be 1, but the function does not actually exist. What type of a discontinuity will we have there? Does anyone know? Oh, by the way, since it's not continuous, it's also not differentiable. All right. Note to self, get new pens. There we go. Yvonne says removable. You probably went over it over. Yeah, so why is it a removable discontinuity? Well, the limit of this, if we use the squeeze theorem, so by squeeze theorem, the limit as x approaches 0 of sine x over x. Did I say that's 0? Did I say that's 1? I think I meant 0. All right, time to verify something. Yeah, no, I was right. It's 1. So it would have a removable discontinuity. It wouldn't be a jump, otherwise limit wouldn't the true limit wouldn't exist. And it's also not a it's not a vertical asymptote either. So it would be a. Actually, what does the graph of that look like? Let me take a look. Thank you, Uzi Time Baby, for the follow. Yeah, you could use L'Hopital's here, but not here. Let's see, what does that graph actually look like? So the graph of sine x over x looks like this. And if I were to zoom in, we approach 1 from both the left and the right, but when x equals 0, this wouldn't equal 1 because we can't have division by 0. So that is a removable discontinuity. Again, yes, you could use L'Hopital here, but you can also prove it by squeeze theorem. Alright, so with that, let's do one more, and then we will call it a night. So we'll say that this is the final problem. So, there are 13 of us in here. So let's see if we can't get... Let's do a quick mad tap to 4.5k likes before we get to the final problem of the night. Yeah, let's do a quick mad tap to 4.5k likes. We only need 700 to get there. So a quick mad tap should get us there very quickly. There's a 1 before sign. Where? Hey, Angle, how's it going? Nope. X's do not cancel here. But I'm not multiplying sine times x. I'm taking the sine of x. So my x's do not cancel. Yeah, no problem, Ty. No problem at all. What type of math is this? This is calculus. This is calculus. While we mad tap, I understand that in order to be differentiable, it needs to be continuous. Yep, but just because it's continuous doesn't necessarily mean it's differentiable. But if it's differentiable, it's automatically continuous. Is it differentiable? This one? No, it is not. Because it's not continuous at x equals 0. So, we've hit 4.5k. So let's look at our final problem of the evening. So, if it's differentiable, it is continuous. Not other way around. Correct. It's still differentiable. It just has jump. Nope. So in order for it to be continuous, it has to be... No, in order for it to be differentiable, it has to be continuous. Because differentiability implies continuity. And even if that were the case, this would actually be a removable discontinuity. A jump discontinuity would look something like this. So a jump discontinuity would do like this. Nope, that should be an open dot. There we go. Something like that would be a jump discontinuity. So yeah, let's get into the final problem. So, and for this one, I'm going to add a little bit of complexity, but I think you all can do it. So f of x is equal to the following piecewise function. Oh, this should be -1. -1, -1. All right. Is f of x continuous at x equals 1 or -1, x equals -1, and is f of x differentiable at x equals -1. In your opinion, is related rates the hardest part of AP Calc AB? It's definitely one of the most, if not the most, difficult. And it really comes down to remembering your formulas and being able to break down word problems. Thank you, user, for the follow. All right, so here are my two questions. Is f of x continuous at x equals 1? And is f of x differentiable at x equals -1? So let's start by figuring out continuity. So what I'm going to do is I'm going to plug in -1 into both of these values. If these two are equal, then it's going to be continuous. Thank you, Yigermall123, for the follow. So I have -1 all squared plus a -1 minus 3. And I want to know if that equals -1, -1 minus 4. Why is calculus for business operations so hard? I thought it would be easier than calculus. So calculus for business is usually more word problem heavy. So again, it comes down to how well can you break down the word problem. And I think a lot of people struggle with breaking down word problems. Or at least that's just my personal experience. Imperfect says they're both equal. If they are, what would they equal? So are they equal? And if they are, what would they both equal? DJ says they both equal -3. Imperfect says -3. Yeah. So let's see if they're right. -1 all squared is -1 times -1, which is 1. Plus a -1 is 1 minus 1, minus 3. And then negative times -1, -1 is +1, minus 4. 1 minus 1 is 0. 0 minus 3 is -3. And 1 minus 4 is also -3. So is f continuous? Yes, it is. Now, is it differentiable? So how would I test for differentiability? Well, actually, I did that the wrong way, but it does end up being continuous. So here's what I'm going to do. Now, let's run this. Let's check by running this through the 3 conditions. So condition 1, does f of 1 exist? Or f of -1? Well, f of -1, because my inequality is greater than or equal to, f of 1 is going to be a part of this first first equation. So yeah, f of negative 1 does exist. So we just test. So does the limit exist? Ty says no. Imperfect says no. Is that for the differentiability question, or is that for something else? Thank you, Jasmine, for the follow. Oh, differentiability. Okay, I'm going to get to that in a moment. So, does the limit as x approaches c of f of x exist? Well, the limit from the left is going to be, so limit as x approaches negative 1 from the right of f of x would be negative x minus 4 would equal negative 1 minus negative 1, so that's plus 1 minus 4, which is negative 3. And then the limit as x approaches negative 1 from the left of f of x would be negative 1 all squared minus or plus negative 1 minus 3, which we also said was negative 3. So condition 2 is true. And 3, does the limit equal the actual value? Well, that's what we tested here. So yeah. So it is continuous. Now, to test for differentiability, I'm going to take the derivative of both pieces of my function, and I'm going to run the continuity test on it. So what I'm going to do is I'm going to take the derivative of x squared plus x minus 3. What would the derivative of that be? Thank you, Sasquatch Andy, for the follow. What is the derivative of x squared plus x minus 3? It's differentiable if both sides limits are the same value and it's continuous, right? Not necessarily. But we're testing, but it would be continuous. Yeah, so the derivative of x squared, take the 2, move it out front, and subtract 1 from the exponent. So that would be 2x. Derivative of x, remember, variable without an exponent is the same as variable to the first. Take the 1, move it out front, subtract 1 from the exponent. So I have 1, x to the 1 minus 1, which is 0. And then the derivative of negative 3, well, there's no variable there, so this is a constant. The derivative is 0 for all constants. So this is going to be for x, still greater than or less than negative, or greater than or equal to negative 1. Now, what about the derivative of negative x minus 4? Hey CJ, how's it going? Hello, what problems are you focusing on today? Today we're going over differentiability. Ben says negative 1. Rainbow Monkey says negative 1. Mohammed says negative 1. Yeah, so here, take my 1, move it out front, subtract 1 from the exponent. So I have 1, or negative 1, times x to the 1 minus 1, which is 0. And then derivative of negative 4. Negative 4 is a constant, so its derivative is 0. So it's going to be x less than 0. Or negative 1. Okay? So now we're going to run the 3 conditions of continuity again and see if we end up with a result. If this is continuous, then it's differentiable. So, does f of negative 1 exist? Well, here, I plug in negative 1 because x is equal to negative 1 on this top piece of the piecewise function. So I have 2 times negative 1 plus 1. 2 times negative 1 is negative 2. Negative 2 plus 1 is negative 1. So f of c exists, so we can check that. The limit as x approaches c of f of x exists. So if I plug in So limit as x approaches -1 from the left of f of x means I plug in -1 to here. So that's just -1 because I have nowhere to plug that in. And then the limit as x approaches -1 from the right of f of x would be 2 times -1 minus 1 plus 1. And as we agreed, that is -1. So because the limit from the left equals the limit from the right, the limit exists. And then, does the limit equal a value? Yes, it does. Thank you, Angel, for the follow. Do you do chemistry? I do not. It has been almost 20 years since I've done chemistry. But I do know someone who does, and I'm drawing a blank as to what her TikTok account is. I think it's like Professor TK or something like that. But yeah, so since we meet all three conditions of continuity, is it differentiable? Yes, it is. It is a line up to -1, then an incline. Yeah. So, with that, we'll go ahead and call it a night. But before I go, I have some things I want to plug. I'm sorry to hear that, Julio. I am really sorry to hear that. So, here, as I said before, all of my lives are going to end up here at this channel. And down below is the set of all actions to take once you get to this channel. And then if you want to follow me here on TikTok, you can follow me. You can follow me at Robert the AP Math Guy. And speaking of TikTok, there are a couple other channels that I highly recommend that you follow. First is ACG Math Tutoring. She's really good at getting people ready for the ASVAB, the Accuplacer, GED, the TEAS test, as well as if you need a review for algebra and geometry. In fact, if it weren't for Audrey at ACG Math Tutoring, I wouldn't even be on TikTok right now. So definitely give her a follow. As well, I recommend Learning with Lynette as well. She's actually live right now. So as soon as I am done here, while I download this live and get it ready to upload over here, I'm gonna be in this live. So she does a really good job with the abacus. So if you jump into her live, feel free to let her know that Robert sent you. Also, I offer online math tutoring. So I offer group tutoring and one-on-one online tutoring. So for group tutoring, I offer it to groups of 3 to 10 students who are all taking the same class at the same time. Now that doesn't mean that you have to take it with the same teacher or even at the same school. All it means is that you are taking the same class at the same time. So let's say you and 4 of your friends are all taking geometry. Then you can sign up for group tutoring. And for this school year only, for the 2025-26 school year, I'm charging $35 per hour per person for group tutoring. And then, as far as one-on-one tutoring, my rate is based off how often you want to meet, how long you want each session to be. And so if you're interested in either one of these, feel free to DM me here on TikTok, and we can schedule a free consultation. And here, down below, is all the subjects that I currently tutor. So I tutor Algebra 1 and 2, Geometry, both regular and AP Pre-Calc. That does include honors. And then I also teach AP. I also tutor regular and AP Stats. All 3 calculus classes. Both AB and BC calculus, as well as differential equations and linear algebra. So with that, I'm so happy the 3 criteria for continuity are in my head. I can't wait till I get into this in class. Awesome, Jay. Yeah, definitely. You'll be a step ahead of everyone. Nice refresher. Thank you, Ty. So it's actually funny that you mentioned ChatGPT. I have plugged in many problems to ChatGPT. It gets the problems wrong, and it still does get the questions wrong. So, and yes, that is a thing. But the thing is that with tutoring, you two, I'm gonna get dinged now that I said it. But over there, you are gonna have, you're gonna, they don't see exactly the problems that you're working on. So, whereas if you do online tutoring, I can help you with the problems that you're working on in real time. Agreed, Jay. Absolutely agreed. So with that, I'm going to go ahead and check to see if I get another reward. No, I don't. All right. So with that, as a tutor myself, seeing people rely on AI equals they don't actually study it. Right. Absolutely. So yeah, with that, I'm going to go ahead and call it a night. I'm going to be jumping into Learning with Lynette's live. If you are interested in jumping in, I will see you there. Otherwise, I will see you all tomorrow at 11:30 p.m. Eastern. Have a great rest of your night, everyone. Bye now.